Good evening and welcome to the ASV's first AstroTalk of 2022. This year is our 100th anniversary and we've got a lot of things planned, including some quite amazing AstroTalks coming up. But tonight we bring you Dr. Alexandra Amon, an astrophysicist from Cambridge University, with her talk on shedding light on the dark universe. But before we begin, I would like to say that in the spirit of reconciliation, the Astronomical Society of Victoria acknowledges the traditional custodians of country throughout Australia and their connections to land, sea and community, and we pay our respect to their elders past and present and extend that respect to all Aboriginal and Torres Strait Islander people today. Tonight's stream is proudly sponsored by Optics Central, and remember, if you're enjoying tonight's stream on Facebook, you can donate stars. Those on YouTube can donate stickers. All donations are welcomed, no matter how large or small they are. And if you're watching us for the first time, don't forget to subscribe and follow our Facebook and YouTube pages. Tonight, before we begin, I'd like to go through a few bits and pieces. Let you know that we have our 100-year centenary raffle up for sale at the moment, which is through Optics Central. The prize kit comes with a Saxon 200 DS Astrophotography Newtonian telescope on a Saxon HEQ5 Pro Go-To mount with a steel tripod, a Saxon Cello HD 12mm eyepiece, a 21mm Saxon eyepiece, and a 25mm Saxon eyepiece valued at around $3,600. All of the funds raised go to the ASV's Remote Observatory STEM project and will be drawn at our Messier Star Party on the 26th of March 2022. It's around 7 p.m. Now, Dr. Alexandra Amon is an astrophysicist based at Cambridge University on a senior Cavelli Fellowship. Her research focuses on cosmology and our understanding of the dark universe, mostly using a tool called weak gravitational lensing. At present, she coordinates the lensing team from the Dark Energy Survey, a large international collaboration. After growing up in Trinidad and Tobago, Dr. Amon studied at the University of Edinburgh and then took a research fellowship at Stanford University. Her doctorate thesis titled Cosmology with the Kilo Degree Lensing Survey won at the Royal Astronomical Society Michael Penston Thesis Prize for the best PhD in the field. In addition, she was a runner-up for the UK's Institute of Physics Jocelyn Bell Burnell Medal for the woman who has made exceptional contributions to the field of physics. Popular in science communication, she has featured on Al Jazeera's The Stream and PBS Ancient Skies. Welcome to our AstroTalk, Alexandra.
Thank you so much for having me. Just making sure you can hear me well.
Yes, we can hear you. Yep, loud and clear.
Great, I'll get started. It is really very much an honor to be able to speak to you all in Australia, because I was actually lucky enough that during my PhD, my second supervisor was based at Swinburne. And so I got to spend quite a lot of my time down there doing observations at the AAT. Now, the work that I'm going to talk about today was mostly done during my postdoc at Stanford University. And now, finally, I'm happily back in the UK. But here are some pictures that I dug up from my first observing trip to Australia. So here's at the top of the dome of the AAT. I'll never forget this sign that said, "Quiet, please, astronomers sleeping," because I was 2 months into my PhD and I thought this was just the best thing. So it really is nice to be able to speak to you all. Now, today I wanted to tell you about the work that I do. So I do my research as part of the Dark Energy Survey. And here's a view of the telescope we use. It's nestled on a mountaintop in the deserts of Chile. And with the images that it captures, our team of experts tries to answer these big questions. So what is our universe made of? How did it evolve to the way that we observe it today? Now, we humans are pretty terrible at imagining and understanding things that we've never experienced personally. So with that, it's not hard to conceive that we have flat earthers or people who cannot accept climate change as a worrying scientific fact. Astrophysicists, however, study the reaches of space and time far beyond human experience. Now, that definitely doesn't mean that we are without our preconceived biases, just that we are exceptionally lucky to be able to practice thinking outside the box, and I hope that you get a chance to do that tonight too. Now, I'm going to start by telling you about some of my favorite moments in cosmology history, so the times when Our discoveries of the universe made us think outside the box and scratch our heads. And I have a very biased opinion, but astronomy or cosmology, like no other field, I think, has this history of totally turning our views upside down and defying our expectations or altering the way we view our existence and our place in the universe. Now, I'll tell you where the field of cosmology stands now, and finally about the Dark Energy Survey, what we do, how we do it, and what we've learned so far. So let's jump right in. First of my favorite head-scratching moments starts way back, and that's in the 1500s with Copernicus. So I don't know if anybody of you, I'm sure you're all familiar with this, but Copernicus debunked this humans' egocentric thinking that the Earth was the center of everything we knew, and that the stars in the night sky revolved around our planet. And this was very controversial and brave at the time when astronomy and religion were closely tied. But thanks to him, initially, now we know that the sun sits at the center of our solar system and that the Earth is the third planet outward of 8, making its journey round and round the sun. We also know that even our sun is pretty unremarkable in the class of stars. It's not really different to any other that we can see in the night sky other than being so near to us. Now, another revelation came from someone who we've definitely all heard of, Albert Einstein, and he rewrote our understanding of gravity, the very law that governs everything that we know. So at the time, scientists were very content that if you had an apple and then you let it go, it would hit the floor. Or if I threw a ball, we could predict the arc that it would traverse when hurled through the air and exactly the position and speed that it would land with. And that's motion governed by gravity. Now, Isaac Newton's theory of gravity, the universal law of gravitation, had stood up to every observation that we were making on Earth. But when astronomers started looking further away at larger scales and more extreme environments than here on Earth, we started to see cracks in this theory. So Newton's law couldn't quite explain, for example, the orbit of Mercury. And so Einstein proposed this alternative theory for gravity, general relativity. Now, let's take ourselves back to that time. Modifying the laws of gravity, we definitely needed evidence for this. I'm sure it came as a bit of a shock. Now, Einstein proposed that any object with a mass, whether it's a planet or an entire galaxy cluster, distorts the very fabric of our universe, space and time, as depicted here. Now, as a result, the light from faraway objects gets bent as it travels across space-time by massive objects. So he claimed that we would be able to see stars that were in fact behind the sun because their lights would be bent due to the mass of the sun. And this would be the ultimate test of his theory. Now, there is a caveat to that because when the sun's there, how would you see things that are less bright behind it? So that was a bit of a hitch until, of course, you consider an eclipse. So in 1919, during a solar eclipse, teams set out to test this theory, and they found that he was right. So his theory of gravity still stands today, and here were the New York Times headlines at the time. So stars not where they seemed or where they were calculated to be, but nobody need worry. So while general relativity is the bread and butter of an astrophysics degree today, back in 1919, this was a blow to the way we understood our universe. Some years on, Edwin Hubble was the face of the next shakeup in humans' understanding. So he was equipped with the Hooker telescope with its 100-inch mirror on top of Mount Wilson, California. And he used the telescope's state-of-the-art light gathering power to take a series of photographs of the great nebula Andromeda. Now, for the first time, the images revealed faint stars in the nebula, and that's shown in this image on the left-hand side here. And Hubble calculated that the stars were at least 10 times further away than the furthest stars in the Milky Way. Aha. So the Andromeda Nebula was really the Andromeda Galaxy. And this discovery implied that other even more faint spirals were probably also galaxies even further away, and they were dubbed island universes. So the belief that our Milky Way was all that there was also went out the window. To boast the advancements in technology, here's a state-of-the-art view of Andromeda Galaxy, or M31, our nearest neighbor to the Milky Way. So we can safely say our imaging has come a long way. Now, in the early 1970s, there was yet another blow to the field, and this one is my personal favorite. Vera Rubin set out to study the motions of stars in spiral galaxies. So the idea is the faster the stars are swirling around, the more gravity you need to keep them glued into that structure. So what did she think that she would see? She expected that stars at the edge of the galaxy would be rotating slower than those near the center. So it's kind of like if the Earth was further from the sun, it would feel a force, it would feel less of a force of the sun's gravity, and it would rotate more slowly. So instead, what she found was something quite strange. Outer stars were traveling just as fast as the inner stars. So what's more, she observed that they were traveling more quickly than she would have expected. So if we could count up all the stars in the galaxy and deduce the mass of the galaxy, and therefore predict its gravity, it seemed that the gravity wouldn't be strong enough to be able to hold these stars together. The stars should be flying apart. And this could only mean one thing, and that would be that there was some invisible mass that we aren't seeing that's creating enough gravity to glue everything together. And that's dark matter. So I love this photo because not only did Vera Rubin redefine our understanding of the universe, but she, for me at least, redefined the idea of what a scientist looks like. And we now know that dark matter comprises more than 3/4 of the mass in almost all galaxies, and it forms this big stable halo in which the light and the visible galaxy live. And thanks to gravity, dark matter acts as the glue to hold all the stars together. Fast forward another decade or two, in 1995, humans' minds boggled with the exquisite Hubble Deep Field. So people must have thought the director of Hubble Space Telescope was mad. So the Space Telescope was launched into space, and the director wanted to use his very special director's time on the best tool that we had in the field to look at absolutely nothing. So he insisted that Hubble Space Telescope spend 100 hours over 10 days pointing at a tiny patch of sky about 1/30th as wide as the moon, near the Big Dipper's handle that was totally dark. There was nothing there that he wanted to see. Now, the Space Telescope's images changed the field again, because of course, what you're looking at is what was found. So after looking for long enough and collecting enough light over time, the Space Telescope found more than 3,000 galaxies in that tiny smidgen of sky. And this image is absolutely teeming with spiral, elliptical, irregular galaxies, proving once again that it is impossible to comprehend the magnitude of the universe without some serious head scratching and maybe some quiet thinking about how majestic it is. And starting with these observations, we now think that the universe contains about 100 billion galaxies, and our Milky Way is just one of them. Finally, and this is my last one, as recently as 1998, astronomers studied supernova, the cataclysmic end of a star's life, to determine how far away the host galaxies were. And you see, supernova always happen at the same point in a star's life when they're at a specific luminosity. And so it's quite like when you see streetlights on a dark path, our brains know that they should be the same. And so we use that fact to calibrate how far away the streetlights are. It's the same with the host galaxy. We call them standard rulers in our universe. And what two teams found in 1998 still boggles us today. And that the universe was expanding, and the expansion was getting faster and faster every day. So we had an accelerated expansion of our universe. And we attribute this phenomenon to dark energy. This is a mysterious component that makes up most of all there is in our universe, and not to be confused with dark matter. So where does that leave us of our understanding of the universe today? Well, we know that everything that we are familiar with, the stars, the planets, the gases, so things we also can't see, like gas, they make up only 5% of everything that there is in our universe. So about 1/4 of the stuff is dark matter, and more than 2/3 is dark energy. And you see, time and time again, the universe has surprised us. None of these ideas were expected or even accepted easily. They often came with wild resistance, but slowly through the power of science, logic, and reason, they were proven to be true. And so I wanted to open with that because now I'm hoping that I've convinced you that we must keep an open mind when thinking about the universe, and more importantly, that we have to let the data do the talking and trust what the science and the peer-reviewed research is telling us. So with that, I can tell you more about the model for the universe that we have today. And we cosmologists try to understand the story of our universe. And I think that there are some pieces of this puzzle that we do understand pretty well. So we know that 13.8 billion years ago, the early universe was just this hot, dense soup of particles with very tiny density fluctuations governed by quantum physics. And the universe underwent this period of rapid expansion called inflation, which left an imprint of the fluctuations at that time. And this bit is important for the rest of the story. We call this the first light of the universe, or the cosmic microwave background. And when we observe it, it gives us a map of fluctuations in temperature and density from the early universe. So a snippet of that map is shown in the bottom left here, a snippet of the cosmic microwave background map as measured by the Planck telescope. Now we know that the expansion of the universe marched on, and those fluctuations cooled and expanded such that they seeded the large-scale structure that we observe today. And the parts that were most dense formed the first clumps of particles, eventually the first stars and galaxies, and today perhaps the biggest galaxy clusters. So that random pattern in the cosmic microwave background is responsible for the pattern of large-scale structure that we observe in the cosmic web today. And so you can see a snippet of the cosmic web, or a simulation of the cosmic web, now in the bottom left instead. And we know right now that the universe's expansion is getting faster and faster every day, and we attribute that to this to a universe that is dominated by dark energy. So we know that our universe is a cosmic web, and it has dark matter clusters and filaments that form the bones of the universe upon which galaxies live. So in the simulation shown here, the complex web structures of dark matter are shown in black, and it guides the location of relatively rare clumps of baryonic or normal matter, such as stars or galaxies, shown in orange. And it's quite like Christmas lights wrapped around a dark matter scaffolding. So dark matter does this job of gluing together galaxies, and it's crucial to the formation of structure. And dark matter's evil sister, dark energy, undoes that good work. So it pulls the structures further and further apart, driving the accelerated expansion of our universe. Now, dark matter and dark energy may seem like hocus pocus, or even something that we here on Earth just don't really need to care about. But without them, our universe would not have evolved to the way that we observe it today. You see, our universe was concocted with the most precise recipe. I don't know if any of you bake, but unlike how I do, for the universe, there is no imprecise dash of this or handful of that, and there's definitely no recipe replacements. So without a certain amount of dark matter, there would have not been enough mass in the early stages of the universe to seed the structures of galaxies, which became comfortable hosts for planets like our own. And without a specific percentage of dark energy, there would have been too much structure. So without dark matter and dark energy and their cosmic battle, we simply would not exist. And so this is the foundation of our dark universe. So it's well described by our Standard Model of Cosmology. And using just a handful of parameters, we can describe the evolution of our universe exceptionally well. So we can make all kinds of measurements of our universe, whether it's exploding stars or bending light or mapping the velocities of galaxies or measuring the first light of the universe as it was 13 billion years ago. And that's really quite remarkable that in our insignificant snippet of this story of the universe, we can make all these different observations that mostly fit a consistent model. Now, of course, there is an elephant in the room, and that is, what is dark matter and dark energy? Well, we don't really know. So there are fascinating and intricate experiments all around the world, and particle physicists are on the hunt for a dark matter particle. And we have pretty good ideas and models and educated guesses for what we're looking for. But the fact remains that the particle has not been detected, and dark energy remains even more elusive. So cosmologists tackle this from a different angle. By studying the galaxies in our universe, we can tell you where the dark matter is, and we know how it behaves with normal matter with respect to gravity. In fact, we know that it wouldn't interact with normal matter or with light, so there could be dark matter particles flying through us right now. And we can tell you how much dark energy there is as well. So despite the elephant, our model holds up pretty well to whatever cosmological measurements we're throwing at it. And we're getting better at making instruments and doing our experiments. So we just keep throwing things at this model, and in hope that we find cracks or rework the structure of our model to give us more understanding. But how do we learn about something that is invisible? And the answer to that is weak gravitational lensing. And that is finally where I come in. So imagine a faraway galaxy. Now its light is traveling across the universe and it gets bent because clumps of matter distort that fabric of the universe, the fabric of space-time, and the path that the light is traveling along gets distorted with it. So that means that every image we take is slightly distorted with the imprint of the cosmos between us and that galaxy or the thing in that image. So galaxies whose light travel past the same structures of the universe acquire coherent distortions and alignments. So if we can measure them with extreme precision, then we get an understanding of the chunk of the universe that the light passed through. And so the more far away the galaxy is, the more distant the galaxy is, the more stuff that it had to pass through. So we wouldn't expect an object that's right next to our planet to have any lensing, but our faraway objects certainly see this effect, this distortion. And so the gravity of the structure in the universe acts like a lens. So much like our glasses, do, we're doing it to background galaxies. So hence we call it gravitational lensing. And the effect on our images is very small. So that's why we call it weak gravitational lensing. So small that we wouldn't notice these changes with our eyes for a single galaxy. We need many galaxies and a statistical sample. And we use weak lensing to tell us where the dark matter is. It's like our eyes can only see the light and only detect the light in the galaxies, but lensing lets us put on these special glasses that reveal where the invisible mass really is, or where the dark matter is. Now imagine that we had really beautiful imaging data covering huge chunks of our night sky. So if we didn't just target a single galaxy, but mapped the large-scale structure over a significant portion of the sky, a significant area. And let's take the diagram above. And it's a simulation box of a toy universe. And the far away is at the back of the image, and the image plane is at the front on the right-hand side here. Now, the yellow galaxies travel through the structure of the universe, the red structure, so that they end up on our image plane. And those that travel through the similar structure in this box appear to have coherent alignments when we observe them. So their images are telling us about the chunk of the simulation that the light passed through. Now, we don't want to just make maps of the dark matter and pretty pictures. We use weak lensing to test that standard model of cosmology. It tells us how much dark matter there is and how clumpy that dark matter is. So it tells us about the amount of structure in the universe. What if we could take that simulation box and slice it along the line of sight? So now, depending on how far away the galaxy is, we've sliced up our experiment. Then we learn about how the structure is evolving over time. So we could use the light from faraway galaxies and the technique of weak gravitational lensing to pin down the parameters that describe both dark matter and dark energy. And here's one more story, one that I'm working on, that I secretly hope ends like all of the others that we talked about at the start, with unexpected results that force us to think a little bit harder. So let's go back to this picture. The gold standard experiment in our field right now comes from the cosmic microwave background, or the CMB. So the Planck satellite was launched into space, and it allowed us to peer back to the very beginning of time, a mere 380,000 years after the Big Bang. And it delivered this map of minuscule temperature fluctuations, and a snippet of that is shown on the left. Now, compared to predictions of our standard model, the measurements of this cosmic microwave background experiment are an exquisite fit. So my research, on the other hand, focuses on the late time universe. And we're probing the current era that's dominated by dark energy, indicated by this purple rectangle. And what we're hoping is that when we compare our observations to the same model that is so well measured by the cosmic microwave background, we're creating quite a beautiful end-to-end test. So we're saying, can we use the same picture that fits the seeds of our universe to describe the vast structures that formed 13.8 billion years later? So it's quite like having a baby picture that's in extremely high resolution, and until now, with the limitations in technology, only a very blurry adult picture. And we're trying to see both if the adult is the same person or the same model, the same DNA, but we also want to understand what happened along the way in the person's life. So in our case, the evolution of the cosmos. Now, it's a particularly exciting time for cosmology, and let me set the scene for you. Technology has rapidly grown, and with the most powerful telescopes in the world, there are several teams performing weak lensing measurements independently. We use much larger data sets than ever before, and we are desperate to see if what we find is consistent with the model as predicted by the cosmic microwave background, or perhaps we find grand cracks in this grand picture. And that wouldn't be so surprising, right? Because we're expecting a model, our model right now, we're expecting it to be able to predict the universe over the extent of cosmic time. So we're seeing that it can describe the universe when it was a cosmic soup to when it was the way we see it today. Now, here's why it's particularly exciting at the moment in the field. So in this plot, and it's the only plot I think I show, on the x-axis, you're looking at the parameter that we measure with our lensing experiment. So we call it S8, and it's telling us how much structure there is in our universe. So that's what this parameter is and these values. Now, this orange line, this orange data point, is the value of the parameter predicted by the cosmic microwave background. So as measured by Planck, this is what we should expect. Now, the weak lensing experiments are shown in red, blue, and green, the three different teams. And there's something very curious here. None of these measurements disagree with the orange line to any real significance. But statistics tells us that our measurements should fluctuate around the model. And what we see is that all of the lensing experiments come up low. So our late time, our lensing measurements that are looking at the universe as it is today, predict a slightly different model than that the universe dictates, the early universe dictates. So each measurement is sitting about 1 to 3 sigma low compared to Planck for the statisticians in the audience. Now, when we combine the results with another probe called galaxy clustering, that tension can get more significant. So this lowness exists from almost every weak lensing experiment to date. But lensing data has always been pretty challenging to wrangle with. And so only now that we've really started to hone our methods is the evidence building up. Now, what would this mean? It could mean that something is not quite right in our measurements of the early universe. So it could mean that the Planck experiment has done maybe something wrong. But as I said, this is the state of the art of the field, and it's not a statement that I would make very lightly. Now, it could be that the lensing measurements are all missing something, but there are so many different lensing measurements from our three teams. So it would be hard to imagine that they're all missing something. Now, it could be the exciting thing that we need some new physics, some extension to our standard model to be able to explain both the measurements from the early universe and the current universe, the late universe. Now, as lensing is a relatively new field, it's fair to say that our results are under scrutiny. So after years of work as part of the dark energy survey, we just added a new measurement to this plot, and we were super careful. So I'll show you a little bit about what that process was like. So this is where the dark energy survey comes in. Now, I play a leading role in this survey, and we just released the most powerful cosmological, or the most powerful lensing data set until now. And that means that after years of work, we've added a new measurement to that plot. And I'm going to show you a little bit of a taster of what it's like going from late nights at the telescope to one of the most telling measurements that we've made of our standard model. I've lost a little bit of track here. I think my slide got a little mixed up. Okay, so thanks to years of work by many people, we've made a catalogue of the positions, distances to, and shapes of galaxies that we have surveyed. So this field is rapidly advancing. Just a decade ago, cleansing experiments used data sets that spanned areas a few times the size of the moon, boasting hundreds of thousands of galaxies. Now, with the Dark Energy Survey, it's a totally different game. Our data set moves to 1/8 of the night sky that we've imaged, and we've catalogued more than 100 million galaxies. And so with such a powerful data set, not only do our data analysis techniques have to be good, but our model also needs to be robust. And you can see that our map makes a pretty cool laser cut jigsaw puzzle that I'm showing here as well. And I just wanted to flag this other cool thing that the Dark Energy Survey can do. So I don't know if any of you remember the SpaceX Tesla Roadster, but the DES camera can help you find your lost car in space. So here's an image that we took of the Tesla Roadster as it was traveling through space. So this is what it's like getting from images at the telescope to our results. So you take a handful of flights through Santiago and over the mountainous Coquimbo region to La Serena, followed by a rickety ride through the desert, climbing 2,200 meters of Cerro Tololo, and it brings you to the observatory. And up there, it is dry, it is high, and it is smack bang in the middle of nowhere, making it one of the best observing sites in the world. So mountaintops are very thin atmospheres with unobstructed views in all directions, and deserts have less water particles in the atmosphere to distort the images as they make their last step towards our telescopes. And so the remoteness of where this telescope is, it ensures that there is minimal light pollution, and so we have a truly dark sky. And this is why this spot is so unique. And so this is another view of the observatory up there. There are many domes on the mountaintop, but the one that we use sits right at the top. And at the summit, it is totally otherworldly. So walking around, even in the day, this barren land feels quite like another planet. Oops. So the Victor Blanco telescope, the one that we use in the Dark Energy Survey, has its the Dark Energy camera is fixed in. It stands the tallest on the summit, and it is simply gigantic. So you can see me there, very excited at our first glimpse of the telescope for scale. And its aperture and primary mirror is 4 meters, and it sits on the 4th story of the dome. And the telescopes run under the basic principle that if you put a bigger bucket of water in the rain, you'll collect more rainwater. So the bigger the aperture or the primary mirror, the bigger the collecting surface for light particles that have traveled across space and time, only to be destroyed by the CCDs of the camera. And so speaking of CCDs, the camera installed on the Blanco that we use in the Dark Energy Survey has a 3.3 foot lens, and it consists of 74 super sensitive CCDs with a whopping total of 570 megapixels. And it allows us to image 3 square degrees of a time to exquisite resolution. So that's an area of the sky about 14 times the size of the full moon that we can image with just one pointing. And DCAM is pretty high maintenance, 24/7. It needs to be cooled by a steady stream of liquid nitrogen to ensure that the CCDs stay at this very healthy minus 100 degrees Celsius. Now, observing life is pretty special. There's an afternoon meeting up at the telescope to make the observing plan for the night. Then you head back down halfway to the lodge, and you have a quick dinner, and then you head back up to the mountaintop again. And once things are ready to go, the observers on the mountain emerge to watch the sun sink below the horizon. This is my favorite part of observing, that there is this tradition. And sunset is pretty spectacular. So humans aren't the only one who've noticed this. This was rumored before I'd been to the telescope, but it is indeed true. The visachas of Cerro Tololo, and you can see one of them here looking something like a mix between a kangaroo and a rabbit, they gather at dusk too. So at sundown at the observatory, both astronomers and researchers alike are wide-eyed and facing west. And the noticeable quiet of the mountaintop is broken a few hours before sunset as the large dome of the Blanco creaks open. And the telescopes look like guardians of the night sky. They're perched on the summit, and these giant robots awaken almost at once to peer into the cosmos. And through the night, they rotate slowly doing their work. And we tow around them with our tiny headlights in the dark, taking what we can to learn from our universe. And so here's an example of our observing room, and a healthy stack of brownies to get us through the night. And here's one of our images. So we're taking images of distant galaxies, and on a full night of observations, we take about 150 exposures. So if we point at each part of the sky for approximately 5 exposures to stack, then we can take an image of 30 different pointings during a single night. And each of them is 3 square degrees, giving us about 90 square degrees that we observe in the night. Now, in each square arc minute, we can image we resolve in our images about 6 good galaxies. So these are good enough for our science. And that means that in one night, we image at least 1 million galaxies in our universe in just one night. And so here's what a stacked and processed exposure looks like. And so remember, 14 moons can fit in this area. And you can see our odd-shaped field of view that the camera has divided into the different CCDs. And when you zoom into these, which we do to make sure the images are looking okay as they come in, you see these beautiful spiral galaxies, and that each of these funny little blobs here are not stars, but of course galaxies, that are just stunning and that probably no one else has looked at. Now, here are some particularly big, beautiful DES galaxies, and you can see that they really do come in all shapes and sizes. So to do a weak lensing analysis and to learn about dark matter and dark energy, we need 3 pieces of information from our images. We need their positions on the sky, we need the shapes of our galaxies, and we need an estimate of their distances, or the distances between us and the galaxy, or the redshift, we call it. And measuring the shapes doesn't really sound so hard. I remember hearing that at the start of my PhD and being like, well, all right. But the galaxies that we're dealing with aren't all the picturesque spirals like the one on the left-hand side here, but rather the fuzzy blobs on the right. So you see the light particles from the galaxy travel all the way across the universe. They get gravitationally lensed by the large-scale structure and encode the secrets of the universe with them, until they get to Earth. So the Earth's atmosphere smears and blurs the image. Then that happens some more thanks to the telescope. And finally, the detectors pixelate the image and there's noise. So even that galaxy now in the top right is a particularly nice one for weak lensing. Measuring the distances to the galaxies is also challenging. So we use the fact that galaxies that are further away have different colors. So ideally, we'd like to obtain a spectra of the light from each galaxy, and that would allow us to break the light into its constituents and see the light profile as a function of wavelength, like these black lines shown here. But that's very expensive to get these types of measurements. So instead, we observe each galaxy with different filters on our camera. So R, I, or Z, and these allow us to pick up different features in the image, and from that we can measure colors and use that to determine distances. So you can see an example here that these 3 galaxies have different types and they're different distances away from us, and so they give different light profiles. And when we make our images in these different filters, we can distinguish the profiles, even if we don't have the full spectra. Now, this all gets more complicated to an effect that we call blending. So as our telescopes get more powerful, we're able to take deeper images of the universe, resolving further away galaxies than previously possible. And that's fantastic, but it also is a challenge because these fields are now crowded and some galaxy images get projected onto others. And so we think we can estimate the redshift, the distance, the redshift to one galaxy and measure its shape. But what do you do when you have about 5 to 7 galaxies that are all on top of each other here? How do you measure something like that? Now, aside from the data, we also need a theoretical model for our measurements. So we use our standard model of cosmology, and we can make predictions for what our measurements should look like. And computer simulations are critical here. So you see, any good school experiment, you do it more than once. You have repetition. And you repeat the experiment, changing different factors in your analysis. Now, that doesn't really work in astronomy because we have just one universe. And so computer simulations bring astronomy back to the laboratory setting. So we can tweak our model, and we can make a universe with a little bit more dark matter or a little bit less dark energy, and see how they change our model, change our universe, and change our predictions for our measurements. And some parts of the model are quite tricky. So we measure how similar galaxy shapes are when they're nearby. But what happens if the galaxy shapes are aligned with each other without weak lensing? What if they're already aligned with each other in reality? So our measurements make the assumption at first principle that the galaxies are randomly shaped and randomly oriented without the effect of weak lensing. And we know that that's not really true. So we need to account for the fact that it's not, because galaxies that form in the same environment may already be similarly aligned and interacting with each other. That would contaminate our signal. So there's, on the left-hand side here, you're seeing two galaxies merging, so they create a natural alignment. And on the right-hand side, we found in one of our images, this chance alignment of galaxies in a row, like a duck, like a row of ducks. And there's another sticking point to our model. So it turns out that galaxies are complicated. So they're not these fuzzy blobs in our images that only obey the rules of dark matter and dark energy. That might be true on large scales, but on smaller scales, there are all these wonderful complex processes happening in a galaxy. So they might have black holes that spew particles out into the universe. And these make our measurements particularly tricky to model at small radii. So these challenges just add to the fun. And the Dark Energy Survey, our large team of scientists from all around the world work on these challenges. And for our last analysis that we just released, we spent more than 3 years working on this analysis with a large team of experts. And I love that about science. It's no longer the idea of a lone man scribbling over parchment, but these groundbreaking experiments that change our understanding of the universe require teamwork from a diverse set of people. And so our international team has worked together to harness data from the night sky and make intricate measurements of faraway galaxies and work through this enormous data set that we've collected. And I wanted to say we aren't the only people in the business. As I said at the start, there were 3 main teams working on this type of experiment. So I started my PhD at the right time when all these surveys were coming online. And I worked as part of the Kilo Degree Survey, which maps a smaller area of the sky, but it does it in more filters. So it gets a cleaner understanding of each galaxy. There's also the Hyper Supreme Cam Survey, which has a very small area, but very deep, beautiful images. And the Dark Energy Survey, its strength is the amount of area that it covers on the sky, just the sheer size of the data set. And our teams work independently, and we have quite different data, and we're doing our analyses blindly. And this is really I think the most compelling part of our results. So we work for 3 years on fake data, essentially. So we make all of our calibration choices and we tweak our model without using the real data. So we never know what the answer is. And then when we've made all of our choices, so we've fine-tuned all of our analysis, then we apply it to the real data and look at the results. And by doing that, we don't bias unconsciously or consciously the results that we might get. And we've all found roughly the same thing. I'll skip this. So going back to this picture, at the time, we had no idea where our data point would lie. And the most important point is that whichever way that I preferred this to turn out, whether I wanted to agree with the early universe or not, it doesn't matter because of this idea of doing our analysis in the blind way. So we don't know for the whole time whether our data supports this consistent story for the universe with the standard model describing measurements billions of years apart, or if we'll find hints at a need for new physics. And a few months ago, this is what we found. So these new green data points were what we released. So they are the smallest data points because we had the most statistically powerful experiment. And in my opinion, these results were tantalizing, but also frustrating, because on their own, like these other two data points, there is not enough compelling evidence that it is so different from the early universe to be a discrepancy in a model, a total flaw in our model. There is just this persistent tension, this hint that they're all low, but nothing that's more than 3 sigma, which is usually the threshold that we take in science for this really being something to look at. But it is compelling that the 3 independent teams are all seeing the same thing, and maybe the combination of them, the combination of our 3 experiments is enough to be a real flaw in our model, to point to a real discrepancy in our model. So how do we learn more? What can we do to go from here? Well, our team is working, first of all, on a very short time scale to combine these results. So we're jointly analyzing the data from the 3 teams. That sounds quite nice. We've already done it with one, and how hard can it be to put them together? But it's actually the first time that these teams have work together to do a joint analysis. We usually work independently and competitively. And so it's really an extremely rewarding experience that we're working together to do a combined result and to see if we have a real tension in our cosmological model. But it won't end with GS. Along with kids in HSC, we're really just the training ground for a bright future of the field. So here is a picture that a friend of mine took when we're standing at the observatory. We're standing at the Des Blanco telescope, and we're looking one mountaintop over. And what we see is Rubin Observatory under construction. So Rubin Observatory will be fantastic, and it will open a new eye to our universe, and it will map the entire southern hemisphere every few nights for 10 years. So it will keep stacking images until it makes a movie, essentially, of the night sky. And it will be a game changer for our field. In just a few years, the year 1 data set will not have 100 million galaxies like we've just released, but more than 1 billion galaxies. To higher redshift, so further away galaxies, and better resolution. And thanks to SLAC, where I worked at Stanford, the team there got the camera up and running, ready to deliver high-resolution images of our universe. And the first image that they took to test it out was on this broccoli. So that was very exciting to see. And shortly after Rubin comes online, we'll also have 2 new space telescopes, the Euclid Space Telescope and the Nancy Grace Roman Space Telescope. And together, these 3 experiments, the combination of their data is actually extremely powerful and special. And that will be exciting. And I think with these incredible advancements in our technology and instruments, there are exciting research prospects in the coming years. And it's really truly hard to imagine what our field will look like in a decade with all of this new data and the discoveries that will come with them. So I'm curious to see how that S8 plot will change during the next years. Certainly it will change. We will either see that we have a consistent universe or that there is evidence of a flaw in our model, in our standard model. But one thing I'm sure of is that there will still be many pieces of the puzzle to solve. So I encourage you to look up and to keep thinking big and to keep asking questions. Thank you.
Wonderful talk, Alex. Now we have a couple of questions. Shahir on YouTube wants to know, when did dark energy come into play? And also, will dark energy prevent the collision of Andromeda and the Milky Way due to the acceleration of the universe? Will it affect the local galaxy supercluster? So it's a three-part question for you to answer there.
Okay, I think I got the second 2 parts. You might have to remind me of the first one. That is an excellent question.
So
do you want to do the first
one was, when did dark energy come into play?
Oh, when did dark energy come into play? We're coincidentally just in the era right now where it has dominated our so the fraction of dark matter to dark energy is like 0.3 to 0.7. So only relatively recently in cosmic scales did dark energy start to dominate our universe. It's always been there, but it's just the amount of matter has been falling off as the universe expanded, the density of matter rather. But that's a great question about the two galaxies, because indeed our galaxy and Andromeda Galaxy are on track to collide in the faraway future. And that is because of their gravitational attraction and potential towards each other. So there are when you consider what a galaxy will do, where it will move in its lifetime, you have to consider a bunch of factors. There's this background expansion, indeed, that's pulling things apart. But for galaxies that live in the same gravitational potential well, or the same vicinity, they are attracting each other with their gravitational forces. So there are usually two components when you try to think about predicting where a galaxy will go. And that gravitational potential for our two galaxies is stronger than the acceleration of the universe. So I guess it slows it down, but it won't prevent it.
There we go. Hopefully that's answered Shahid's question. We have another one from Lee. Not sure if I missed it. Are the DEC sensors color or mono and using filters?
The DEC sensors. So we used filters in our imaging. So we just have photometric imaging, not spectroscopic. And we use, over the night sky, we use GRIZ filters. I'm not sure if that answered your question. In some parts of the sky, we have 9 filters. So we get really nice wavelength coverage, and that helps us understand our survey.
He'll probably understand that, I know, Lee. So Ronald wants to know, how much further will we be able to look with all the new instruments we have?
Ooh, really? Well, so weak lensing surveys, or these large cosmological surveys like Rubin and Euclid and Roman, they prioritize surveys, so wide area of the sky. So they look much further, I'd say about more than a factor of 2, probably more like a factor of 10 deeper images. But if you really want to see the furthest away objects, of course, the JWST experiment that was launched into space over Christmas, that's your best bet. So that doesn't do survey observations, but hones in on specific galaxies much better, so much higher resolution, and in the infrared, and that will really let us see the furthest away objects.
Yeah, we've got a couple more as well. Do neutrinos make a contribution to the observed mass?
If you're this is an expert audience, yes, the neutrinos we have to factor into our model, and there are different choices that you can make. We can say that we don't really know anything about the neutrino mass, and so we keep that as a free parameter in our model. Or you can fix it, which is what some experiments do, to what we think the mass of the neutrinos are. And it does make a slight difference in our results. So we look at the different cases.
Okay, so we got.
I think in the future, we can ask the reverse question, which is one thing that a lot of people are excited about. So when we have our experiments, instead of treating that as a nuisance parameter, I think in the future, what we're hoping to do is to be able to learn about the neutrinos using these data.
The last one, Steve Johnson. Great talk, Alexandra. Does dark energy explain or partly explain Einstein's cosmological constant in his theory of general relativity, which he added to keep the universe from collapsing inward?
Excellent question. I should have said this. Yeah, so the theoretical idea for what dark energy is. So there are a few different ideas that came up at different times. So first was Einstein's cosmological constant, this extra factor in his equations of general relativity. It was put in for different reasons, as the person who asked the question said, but now it can explain an accelerating universe. And then the observations that our universe is accelerating, we call that due to dark energy. So our best bet for what dark energy is a cosmological constant by Einstein, which is associated with a vacuum energy, the energy that exists in a vacuum. So this is our best theory of what dark energy is right now.
2 more questions have snuck in. We'll get those 2 and then we'll wrap it up for you. I once read about the universe may not be overall isotropic, but the survey also does not have a significant sigma to confirm. So the universe being isotropic might not be one that you can answer. So
on the largest scales, we make the assumption that our universe is homogeneous and isotropic. So indeed, when we were doing our experiments let's say 10 years ago, or when my PhD advisor was doing their experiment 10 years ago, they were looking at just a small patch of our sky. And then if you got different results, indeed, you would be like, well, maybe that's just because that small patch of sky is not quite homogeneous, and we're not surveying enough area. And so that's making a difference in our results. I think now that we're looking at 1/8 of the night sky, and in the coming years when we're looking at the entire southern hemisphere, then I think our assumption that the universe is homogeneous holds up, or that can no longer be something that we question in impacting our results.
We've got one last one. There are more questions. So it's up to you if you want to answer some more questions, but there are some more popping up. But I've got one last one at the moment. Sure. Brenton wants to know, well, he said great talk, but he also wants to know, how is the image processing done? Is it all automatic?
That's an excellent question. The pipelines are semi-automatic, I say. So each stage is push of a button. So we code up these intricate pipelines, and we usually make our pipelines public at some point. Actually, I should have said that yesterday was a very special day because we made all of the dark energy survey data public, which was a real landmark. So everything that we use to make our cosmology results now exists online if you Google the dark energy survey data release. So anyone can play with this data, which is, I think, the best part of doing these experiments, that anyone can have it. So our pipelines are semi-automatic, I say. We build them as best as we can. We're not computer scientists. It would be much better if we were for this aspect. And so each stage, like removing the impact of the atmosphere, would be a pipeline that we run on the entire data set, and that would take 3 days. And then we do the next step and it runs. So I guess there's a middle ground.
Wonderful. Now, did you want to answer the last two questions?
Sure, yeah.
Okay, so Rodoc on YouTube wants to know, is the cosmological constant changing over time, and how do you account for that?
Okay, so the cosmological constant isn't changing over time, so it's constant. But what if you think of it, there's a trade-off between the amount of matter and the dark energy density. So there's two different things. As your universe is expanding, the amount of matter isn't changing either. But the volume of the universe is expanding. And so the relative amount of matter is falling off. The dark energy, the cosmological constant stays the same. So at some point in time, you start having more of the cosmological constant than the matter density. And so that's how come we were in a stage of the universe a long time ago when matter was dominated. And now we're in this stage where dark energy is dominated. And so that's why we think we've started accelerating. We've started an accelerated expansion.
And Slumo wants to know, could the tension between the CMB measurement and your measurements be similar to the tension between the CMB and local measurements of the Hubble constant?
So this is the question. Yeah, so I have not... Sorry?
You got some good questions being thrown at you.
I got excellent questions. I'm very impressed. So a major talking point in our field right now is this Hubble tension that is a higher significance than what we are seeing. That's about 5 to 6 sigma, depending on who you ask. And indeed, it's a very similar story where there are measurements of the late time universe that are seeing something different compared to the early universe or Planck experiment. And I think that the significance of that tension kind of makes our tension that is slowly coming up behind it more fascinating, because there have been lots of theory papers trying to understand, could they be the same thing? Is there some different fabulous model for our universe that would explain both? And it is quite hard to come up with a theory for the universe that would explain both those tensions. I think what some people hope that it points to is that the early universe experiment has done something wrong, maybe. Or there are still people that say that both the Hubble tension late time experiments and my own type of experiment is missing something. Yeah, but certainly the two tensions at once, the two discrepancies at once, are what is quite exciting for the field right now.
Well, Dr. Alexandra Ammon, thank you very much for joining us on our stream.
Thank you for having me.
You're welcome. We're glad to have you on board as our first presenter for 2022. Before I go, I just want to mention to our members, that we have our 100-year anniversary tickets on sale. Actually, even to the general public, the raffle is open to everybody. Tickets are on sale. Links on our Facebook page, on our Instagram, on our websites. Same with the our calendar, our ASV calendar, our 100th-year anniversary calendar with images produced by our own astrophotographers. They are on sale as well. Links available again on our Facebook page, website, and our Instagram pages. We have the library. ASV members, the library is open tomorrow. You can, once again, book your tickets through Eventbrite. The links are in all of the usual places, Crux Extra, on the website, and our members' forums. Thank you, everybody, for joining us for our first stream of 2022. We hope you enjoyed tonight's Astro Talk. I know I did, and from the comments, it looks like everybody else did as well. Remember, if you're not a member of the ASV and you're interested in becoming one, go to www.asv.org.au/join. And if you don't follow us on Facebook, hit the follow button. And if you don't follow us on YouTube, please hit the subscribe button. And we'd like to thank you all, and we'll see you for our next live stream. Hopefully, we will be doing a Deep Sky one in a few weeks' time. Thank you, and we'll see you later.
Thank you.